Hi guys, this is the video that has all the slides and notes for section 17.2 on masses of atoms. We'll start with this section here. This is the big idea is that atoms have almost all of their mass in the nucleus. The electron cloud doesn't really count because the electrons are 2,000 times lighter than protons and neutrons. And so what you almost want to think of is this tiny little nucleus, right? And then the electrons are much, much further away. For example, if the nucleus were the size of a golf ball, the electrons would be a mile and a half away, maybe even 2 miles away. And so you've got to think of this tiny, tiny nucleus buried in the heart of the atom. And then the electrons are almost like this invisible force field that are much, much further out, right? Anyway, this slide summarizes everything. It's certainly not to scale, is it? But it summarizes the charge and mass of protons, neutrons, and electrons. And so you should be familiar with that. This slide is a little bit denser. There's just more here. Again, the idea is that neutrons and protons weigh about the same. It's good enough for government work. But both of them, they put a proton on this picture, but they could just as easily have put a neutron, are many, many times heavier, pretty near 2,000 times heavier than electrons, right? You've got a whole bunch of information packed into this chart. So you get the name of the particle, you get the symbol of the particle, you get the charge of the particle. In this case, 0 means no charge at all. The neutrons are neutral. Where they are found in the atom. Here's their charge, 0 again meaning neutral. Mass, now you'll notice a $10 word right here, AMU. That's brand new. AMU stands for atomic mass unit. And the thing to take away here is that protons weigh exactly 1 AMU. Well, I shouldn't say exactly, about 1 AMU. Neutrons weigh about 1 AMU. Electrons are much, much lighter, approximately 0. They're so light that we ignore them. And then it gives their actual mass in grams. All you have to appreciate here is that these numbers are incredibly small. This means you would have to move the decimal to the left 24 times. This means you would have to move the decimal to the left 28 times. So they're numbers that are just beyond human understanding. All right, so you're introduced to a whole bunch of vocabulary in this slide. The first is atomic number. It's got the symbol Z. Don't ask me why, I'm really not sure. It also tells, well, its job, I should say, is to tell us the number of protons. So atomic number is a fancy $10 word for number of protons. In a neutral atom, it also tells you the number of electrons, and you can see that down here in the example with carbon. The atomic number is 6. That counts 6 protons. It also counts 6 electrons. You say, hey, kiddo, it's also the number of neutrons. That's generally not true. It's an accident that in this picture, the number of electrons is also 6. In general, these three numbers are not all the same. Protons and electrons will be, neutrons will not be the same. All right, another new term, mass number. Well, here's your definition right here. You take everything in the nucleus, you count up how many protons and neutrons, and that's your number. Has the letter A. Again, I'm not quite sure what that's all about. Here's the example. For carbon, that means there are 6 protons, 6 neutrons, 6 plus 6 adds up to 12. Here's another example for helium. 2 protons, 2 neutrons, that adds up to 4. Say, Kato, you just told us that in general the numbers of protons and neutrons are not the same. They're not. For small atoms they are, but as soon as you start getting a little bigger, that stops being the case. You can't depend on A always being double Z. And then finally, this big X is C for carbon or He for helium. It's the chemical symbol for whatever the element happens to be. So take a look at this slide. Make sure you're familiar with the letters. Make sure you're familiar with the the $10 words there, and you know what they mean. So one of the things you'll be asked to do is calculate neutrons, and it's not hard to do, you just have to know how to do it. In general, it's a two-step process. The first step is when you're looking at a box on the periodic table, you take the big number, you subtract the little number. The only thing you have to do is you got to round this big number. And usually that's pretty straightforward. There might be a couple examples where the rounding gets a little sketchy, but I'm going to try to avoid those and make sure I'm giving you examples that are very straightforward. So in this case, our big number is 12, our little number is 6, and you just take the difference, right? So it's big, take away little. And you say, okay, why is this a decimal number? It's a decimal number because of something called isotopes that we'll get into in a bit here. But for calculating neutrons, don't worry about it. Big number, take away little number, round it. All right, so here are isotopes. If you look at these, you'll notice every single one of them has one proton. One proton, and over here, one proton. P's are for proton. That means every single one of these is hydrogen. Right? You may recall protons give identity. So every single atom in the universe with one proton is always hydrogen. What's different, of course, are the number of neutrons, and that is the definition of an isotope. It's two atoms of the same element, hydrogen, 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 that have different numbers of protons. I sort of just misspoke now. I said two atoms of the same element, but there could be more than two. It's at least two atoms of the same element. Same number of protons, different numbers of neutrons. You've got to know the definition. You should understand this notation and know what this means. This is just from the last two slides. You should also be able to draw these or identify these. So protium is the kind of hydrogen that has no neutrons. Deuterium is the kind of hydrogen with one neutron, and tritium has two neutrons. You say, where are these names coming from? Well, tri means three. 1, 2, 3 objects in the nucleus. Deutero means two in ancient Greek. 1, 2 objects in the nucleus. Protium just comes from proton. There's just a proton in the nucleus. Here's a slightly different form of isotope notation. You can see these are all carbon, and they're all carbon because they all have 6 protons. But they're isotopes because they have different numbers of neutrons. This particular kind of carbon has 6 neutrons, right? Big take away little is the number of neutrons. Big take away little leaves us 7 neutrons, so that's a different isotope. Big take away little, 8 neutrons is another isotope of carbon. Sometimes you'll see them written this way, where it's the name of the element, and then a dash, and then the mass number. Name of the element, dash, mass number. Name of the element, dash, mass number. Underneath here, these percents is how common each of these kinds of carbon is. So carbon 12, with 6 protons and 6 neutrons, is by far the most common type of carbon we find in nature. Carbon 13 with 6 protons and 7 neutrons isn't particularly common. You're not likely to find this. And carbon 14 with 6 protons and 8 neutrons is exceedingly rare. You may have heard of carbon 14. It's often used for dating things. And in fact, it does a pretty good job of dating things up to about 50,000 years old. The other stipulation is that those, it's good for dating things that were at one point alive and have died. So these are your notes for section 17.2 on the masses of atoms. This should help you get through any of the homework questions. If you do have any more questions, certainly write to me or ask during one of our meets.